So this is just a screenshot of the problem that we looked at previously, showing the amplification of the electric field across the membrane in the previous problem. So external fields are going to be essentially magnified across this plasma membrane. Now this is related to bioimpedance simulations, where we're interested in the electrical properties of a tissue or a cell suspension. It turns out the apparent current density is a sum of active and reactive current densities here, and this is just the Maxwell displacement term of the current. And it turns out the conductivity is just the active current density divided by the electric field, whereas the permittivity is the reactive current density divided by the electric field times the frequency. And this is modeling. When we do this, we're modeling an AC current module. So I want to look at another problem where we calculate the frequency dependence of these quantities. And I'll remove the previous problem. This is the problem is Maxwell-Wagner. We'll look at the geometry here. It's a little bit more simplified. This is the cytoplasm, the external medium, and the membrane. Once again, is very small conductivity of the membrane. The cytoplasm I've chosen as 78 with electric conductivity of 1, and the external medium has the same conductivity here, which can vary depending on the ionic concentrations and so forth. Now, on the edge labels, this model has axial symmetry. This is the left edge is 1 microvolt, and the I'm sorry, that was the right edge. The left edge is -1 microvolt. And the cylindrical boundary of the model has 0 current density. I've assigned 0 current density here. Okay. One thing you might be able to see is, once again, the model has symmetry about this very middle plane here. And I can further simplify it by creating an additional boundary here, assigning 0 volts, and discarding half of the model. Okay. Now, let's go ahead and solve the problem to see what we are in AC conduction, and the frequency is 10 hertz to begin with. We're going to change the frequency. So let's go ahead and solve for low frequencies, and you can see the field has been screened from the interior of the cell. Now, what I would like to know are the active and reactive current densities as a function of frequencies. And if I just want to look at these components at a particular point in the model, I can choose this tool here and select different points here. So I can use this value selector, and I'll make this a little bigger to illustrate. Okay, so these are the active, the reactive, and the apparent current densities at different regions here, and you can see that they're much smaller inside of the cell than in the external region here. This is 10 to the -7 compared to 10 to the -2. Okay, so in order to look at the frequency dependence, I'm going to choose one plane of the model here, the left boundary, and I'm simply going to calculate the current, the different current components as a function of frequency. So the tool I'm using is the parametric analysis with LabelMover. And I open this. Okay. Now I need to choose a base problem, which is the problem that I have here is Maxwell Wagner. Open this. Now we'll add values. Okay, this is the Add Values window. I'm going to choose the left boundary of the model and look at the active current. Let's add that. Okay. Also, I want to look at the reactive and the apparent current densities. Okay. Now we want to record steps. This is the Record Steps window. And I'm going to change the problem properties. The property that I'm going to change is the frequency. Right now the frequency is at 10 hertz. I'm going to increase the frequency in 200%. Okay, so currently the frequency is 10 hertz. If I increase the frequency 200%, the frequency is now 30. Okay, for the second step. I'm going to repeat this step. So now the frequency is 90. And I continue to repeat. It's now 270. Close to 1 kilohertz. Getting close to 10 kilohertz. Getting close to 100 kilohertz. Over 1 megahertz. Approaching gigahertz. That's half a gigahertz actually. Okay, we're at 1. Okay, that's at 10 gigahertz. Okay. So we repeated it 19 times. Now we're going to get the results. So it's solving the problem. We can see that the active current, roughly 10 to the negative 11. Notice that the reactive current is changing much more rapidly than the active current. So the reactive current is increasing because we have capacitive coupling through the membrane, and currents able to fields are able to penetrate through the membrane at higher frequencies. So the reactive current is changing. The active current is still relatively stable. However, it's the dominant component in the apparent current density, since these two columns are roughly the same. Notice the reactive current is the one that's going to be proportional to the dielectric constant divided by the frequency. Okay, we've solved 16 out of 20 problems. $17 out of 20. Okay. Now what I'd like to do is we can, if you want to take these values and move them over to Excel or MATLAB or MathCAD, you can then extract the different electrical parameters. And we can also plot the results here. And this is actually the active current density. And you can see it was pretty much constant until we're over roughly megahertz, and then we jump up in steps. So the conductivity is actually going to be jumping up in steps here. This is in the beta range. If we look at the reactive current density, it does change more rapidly. However, we really need a log scale in order to see the different variations in the reactive current density. as well as the apparent current density, which is of order magnitude of the previous value.